Hello, thank you so much for welcoming me here. It's lovely to come and talk to you. I was actually asked to do this some time ago when a lot was going on in Iceland, and I said, "Oh, well, June 25, yeah, be fine. We'll know, it'll all have finished, and we'll know all about it, and I'll just be able to summarise it." And of course, it is out of the news now, isn't it? But it's not quite finished. So let's get on. I'm going to talk a little bit about why Iceland is even there and a little bit about how old it is. So a bit of summary, probably many of you will know much of that. Talk about some of the recent eruptions, some of the research that I've been doing in central Iceland, and then a bit about the future and present. Sorry, the present and future, that's the way it goes, isn't it, of Iceland. So, okay, let's get started. So why is Iceland even there and how old is it? Well, everybody knows about plate tectonics, right? It's there because of plate tectonics. And volcanoes are supposed to happen on the edges of plates. And, well, okay, Iceland is sort of on the edge of a plate, isn't it? It's up there, of course. But it's the only lot of volcanoes in that sort of place. So there's obviously something slightly odd going on. Just a reminder, we tend to get volcanoes. Well, let's start over on the left, shall we? We get island arcs. Volcanoes happen along lines in island arcs, close to a trench. Iceland doesn't fit that model. You can have shield volcanoes. Hawaiian arc is the Hawaiian chain of volcanoes, of course, is the best known over a mantle plume. That doesn't really look like Iceland either. You can have oceanic ridges, which of course do have volcanoes, but they don't tend to stick up above the level of the sea. So Iceland sort of is like that, but sort of not. And the other typical type of volcano is on top of continental crust, where you have a line of volcanoes, volcanic arc, and obviously Iceland doesn't fit that either. So it's a bit weird, and people have been arguing about why it is a bit weird and to what extent it is one thing or another. But it clearly is some sort of combination of sitting astride an ocean ridge and a bit of a plume. So there is lots of seismic evidence that there is a plume of some sort beneath Iceland, but it is not quite as convincing as would be nice. It disappears after about 700 kilometers. Most mantle plumes you can see going down very much deeper. It's quite broad. This is a picture I always call the headless cat because that's sort of what it looks like. This is a seismic model. It's quite old now, but it was a model based on seismic evidence of where the plume sort of was. So it's not even a proper plume. It's kind of pulled out in elongated slightly. There is some chemical evidence of a mantle plume, but that isn't really enough to explain everything we see on Iceland. And I think perhaps this picture shows effectively part of the problem, because this, yes, you can see that just about, that's the part of Iceland that's immediately above the plume. And you know that you have volcanoes sort of running from top to bottom of Iceland. But Iceland is very asymmetric, isn't it? So if it were just to do with sitting astride the mid-Atlantic ridge, where you've got this plume as well, why wouldn't it be more symmetric? Why is there so much of it out to the west? Well, this, I hope, goes some way to explain this. This is some relatively recent work that has been done to show where, looking back, so this is using gravity evidence mainly, and various others, magnetic and so on, to look at where the plume has apparently been. So let's just work it backwards. About 60 million years ago, the plume appears to have been on the west coast of what is now Greenland. You have to close up the plate tectonics, okay? So there is no ocean in between, and the Eurasian plate is stuck on the side. Okay, so this line here would have been attached to this line here, more or less, okay, 60 million years ago. So that's where the plume seems to be. Then it seems to wobble around a little bit, and it ends up now at 0 here over on the eastern side of Iceland, which is interesting until you think, oh, hang on a minute, aren't we always told that mantle plumes don't move? Well, we don't really know that over an extended period of time. I've already mentioned that it's a slightly strange plume anyway. So a lot of more complicated work has been done. Just have a look at the thickness of the crust here. We can see a much thicker crust on this spreading part of the ridge here, but also some rather strange stuff going on up here. JMM stands for the Jan Mayen microcontinent. This point here, all right, the big star, that's where we think the plume is now. So it's underneath that eastern part of Iceland, and we've got this Jan Mayen microcontinent, strange bit of thickened crust, weird stuff going up to the northeast. Very, very odd stuff. So let's have a look at a model, and it is only a model, bear in mind, from some work a little while ago now, trying to piece together what has happened. I need to look at this screen, don't I? Okay, so let's go back 55 million years ago. We've got no ocean there, okay? It's all closed up. Look at what we'll call the Iceland hotspot, IH, okay? That's where it is. Now look at the coastline here of what is now Greenland. The window that we're looking at is staying the same through all of these pictures, all right? But if you just look through 55 million years, 52, blah, 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 down to 27 million years, can you see Greenland itself has shifted in that window a bit? Okay, the Eurasian plate has moved a bit, and the hotspot has hardly moved. It's moved a little bit, but hardly at all. Just a model, as I say, but broadly, we're suggesting that the hotspot has more or less stayed there, and the continents have moved across and spread. So there's an awful lot of rather complicated stuff going on. And this little bit here, the Jan Mayen microcontinent, the suggestion is that was on the eastern coast of Greenland, and it sort of slithered off. The hotspot more or less stayed where it was on the side of Greenland, and then really quite recently, let's say 30 million years ago or so, this spreading ridge moved slightly to the left of the hotspot or the plume. So that's the suggestion of what started to happen. The spreading ridge was just happening anyway. Another way of perhaps trying to explain that is you had this microcontinent over, so this is really recently now. We've got the Jan Mayen microcontinent over towards the east now. We've got Greenland over on the west. You've got the microcontinent, quite thick piece of crust there, and the spreading trying to go on to the west of that. And as the whole thing is moving west, as you saw in that earlier slide, the whole thing moving to the west, every now and then, the spreading just dies, and then it jumps a little bit to the east, and then it jumps a little bit to the east. So that's what's happened over relatively recent times, over the last few million years. And the current system is thought to be something like this, where we've got the plume axis under the eastern part of Iceland. So Orfjökull is linked to the very large ice cap in the southeast of Iceland. We've got the East Rift Zone, which is where most of the volcanic activity is happening, and the dying, presumably, Western Rift Zone to the slightly west of that, and the Snæfellsnes flank zone, which is way out to the west of Iceland. So that sort of, I hope, begins to show why Iceland is so asymmetric, even though you'd think if it sat astride the mid-Atlantic ridge, there should be half of it one side and half the other side. So it's because of the complication of the plume. And really, that's the answer. Why is Iceland there? Well, it sits astride the mid-Atlantic ridge, fine. It also sits near hotspot or mantle plume. And it's the interaction of the two. And really, the answer is it's very complicated. And if you wait a little bit longer, there will be some more papers that will show that it's, well, I hope not completely different to that, but that there'll be some other ideas, I'm sure. So how old is it? Well, that's actually quite interesting, because it is, the oldest bit is only 16 million years old. Now, you think of the UK, we've got rocks from all ages almost, but nothing much younger than the British tertiary volcanic province, have we? So 16 million years is the oldest bit, that's way out to the west. But it's actually been inhabited since the year 874. So it has been inhabited for a huge percentage of its existence, more so than the rest of the planet, probably. So it's quite an interesting factet. Okay, so let's talk about some of the recent eruptions, and kind of by definition, they're all recent on Iceland, but we won't talk about all of them. But let's look at this pretty map, and I was sort of the fried egg map, this one, isn't it? Each of those fried eggs is a central volcano, and by central volcano in Iceland, what that means is it's a place where there's evidence for a magma chamber. The evidence being a lot of stuff happens above it. That's most of the evidence. There's very little seismic or other geophysical data for it, but you often see a large caldera structure. But in each case, you've got a very elongated, pretty much north-south structure of dikes, fissures, and stuff that goes on when activity happens at the central volcano. It can happen a very long way away from the volcano as well. This only happens in Iceland. No other place has fried egg volcanoes in this sort of way. But it really is quite extraordinary. And I'll show you some of the work later for volcano number, can you see that?
Yeah.
Oh, good. From volcano 21, which is Askja, where the fissure swarm goes right up to the coast there, and hundreds and hundreds of kilometers away from the main volcano. So you have activity there, and something can happen, as in lava can come out hundreds of kilometers away. And this is one of the massive problems that you have in Iceland when you try to predict what's going to happen next, because so much of it is governed by the dike structure, magma traveling in sheeted complexes beneath the surface. You never quite know if and when they're going to pop up and erupt. So it does make hazard warnings and so on very, very complicated. So let's look at a few eruptions. First of all, I just want to, as well as the complications of the plate tectonics and the plume and it being quite young and all that, very much more recently, it was being covered with ice. And of course, that complicates the situation too. So we started many millions of years ago thinking about where that hot plume was. There was no Iceland there at all. Plate tectonics was getting on with it. It was opening, the northern Atlantic there was opening up. It was all absolutely fine. Only 5 million years ago, this is more or less the outline of Iceland. This R at the bottom here, that is where Reykjavik, the capital city, is now. So 5 million years ago, Reykjavik didn't even exist. The land on which Reykjavik is did not exist. And you can see the older line of the opening plates over on the west there. About 5 million years ago, it had jumped over to what is now the East Rift Zone. And this is the little bit of ice cap that it seems to have had. Then about 1 million years later, it was a bit bigger because it had been erupting, and Reykjavik still didn't exist. And so we can follow that through. So a couple of million years ago, the land mass existed. So there's R, it's just about on land. Oh, but it's all covered in ice. So it spent a huge amount of time under ice. So those volcanoes didn't really stand a chance, did they? First of all, they've got to come up through the sea, and then they're covered in ice anyway. And so the largest extent of the ice cap here, a few 100,000 years ago, covered the entire land mass. The Younger Dryas maximum of ice cap, let's say, finished, what, 10,000 years ago or so. You can see it pretty much covered the whole of Iceland. And now, as I'm sure you know, it has Europe's largest ice cap, shadow of its former self, but that's down in the southeast. Okay, so let's look at a little bit of geology. So instead of fried eggs, we've got beautiful LGBT or something, I don't know, multicolored stripes here. So that Neopol is the big ice cap here. So that's white where that is. But let's go over to the western part. So this is amongst the oldest parts of Iceland. And this is what much of Iceland looks like. If you drive around the outside of it, I mean, really, all you can do is drive around the outside or drive north-south through the middle. It's a bit, well, it's complicated doing either, to be honest. But if you go around the outside, what you will see is lots and lots of these little settlements, pretty coloured buildings, a little bit of a harbour, bit of fishing and stuff going on, and bit of grass, not as much in the way of forests. The mountains aren't really very high, are they? And you know, they do say if you get lost in a forest in Iceland, stand up, then you then you won't be lost. There are some very spectacular features. This here over on the right here, this is called Kyrkfjell, and it was. Can you see that? That's very pretty. It's not a volcano. It looks a bit like a volcano, I suppose. It's a very famous view, this, because it was used in Game of Thrones, Daggerhead or Dagger something. Anyway, it is just a pile of intercalated sediments and quaternary volcanics and so on, a little bit of tertiary lava at the top. So it's just a series of lava flows and so on, and it's just been eroded away. So looks like a volcano, not a volcano. And that's most of Iceland. It's just a pile of lava. What I say just? It's a pile of lavas. And sort of just to emphasize the complication of doing geology in Iceland, this is taken from the Askja volcano right in the middle of Iceland, but it's a rather interesting view because this brown tephra we know was erupted in 1875, and in this case that black stuff was as well. But you can see it's quite thick here. It's almost a meter thick here, and there are some regions where it's even thicker. This ice below it was there before the 1875 eruption, so there is still ice on land. I think that's really cool. There's still ice on land there that is older than 1875, and it has survived this long. Sadly, what with global warming and all, it does seem to be disappearing, and there's an awful lot of sinkholes, and you used to be able to walk across this area quite comfortably and safely 20, 30 years ago when I started working there. It's quite dangerous in some places now because you literally fall through where the ice has now melted. That's just a little extra bit of information there. So Katla is Iceland's most significant volcano. It's probably one of its best kept secrets, because if you asked most people in the UK which is the volcano in Iceland that we should watch out for, they wouldn't say Katla. It has done more damage than any of the others in historic times, and probably will do so again. So there it is. It's down the bottom of Iceland. And what does it look like? Well, it's sort of like the rest of Iceland. It looks like a fissure. It doesn't really have much of a pointy peak, although it is slightly elevated. There are parts of it that are very elevated, or relatively. So this is basically a cinder cone along the ridge there. So in 1783, the Lackey fissure, which is just part of the Katla system, erupted and was very significant. Sorry, I missed out the 939 eruption fissure, all part of the same volcanoes. This is the thing about these fried egg volcanoes. You have the place where the magma is stored, and then the fissures and where you actually see the eruptions occurring can be many, many, many kilometers away. So there's evidence that even this very early eruption had a massive impact on humans. We can see evidence from tree rings in Australia that suggests that there was a climatic impact from this particular eruption. Lackey, I think you've probably all heard plenty about in the past. It's well known that the coldest temperatures ever measured had been in America were immediately following that eruption. Massively hot summer in Europe, followed by a very cold winter as well. That's been linked to all sorts of civil unrest and famines and so on. Pretty significant impact from this little volcano that mostly people have never heard of. A little bit further down to the south, slightly off, the Vestmannaeyjar. So that just means the Westmans Islands. So they're sort of west of most of Iceland, I suppose. Anyway, they're just offshore. So one of them, which many of you will have been alive in 1963, may remember the Cirencester eruption from 14th of November 63 to June the 5th, 1965. It was on the telly. It was quite a big deal at the time, and it was quite pretty, isn't it? So a new island was born. The black stuff coming out of the crater there is phreatomagmatic eruption. So it's a bit of hot magma, and all of this white stuff is steam, mostly seawater. So it erupted away for a period of time and built a beautiful island. More of that later, but much more recently, well, a bit more recently, Eldfell volcano on the island of Heimaey erupted in 1973. So that's another of the Vestman Islands, again, just offshore the south of Iceland. Beautiful little volcano. In this case, the island was a little bit bigger anyway and was already inhabited. So made for some very beautiful shots here of what the impact of the eruption was. These are chimneys sticking out the top of the ash that was erupted, and lava flow coming down the street. This was a fairly early example of mitigation, and I'll come back to mitigation a little bit towards the end, where this was a great example of people trying to do something about this eruption. In the end, it was nobody died. People were evacuated. They were very close to the sea, which did help, and they were able to pump seawater onto the lavas to cool them more rapidly than they would have cooled otherwise. And in fact, they were able to use the lavas, the heat energy within the lavas, to produce hot water for the buildings for some considerable time after the eruption too. But they used seawater pumped on to just try and hold the lavas back. Now, of course, it's very easy with hindsight to say, look, they stopped the eruption. Of course, you don't really know, because you don't know what would have happened if you hadn't done that. But it does look as though that was quite an effective mitigation, and that was quite a long time ago. Mitigation is getting smarter as we go through time, but that was interesting eruption, and a lot learned, and the island was 20% bigger by the time the eruption had finished, so all good. Krafla, coming up here to the north of of Iceland. Now that's where the centre of the fried egg is. That's where the caldera of Krafla is. But you can see its fissure swarms go way up to the north and way down to the south. And what that actually looks like when you're there is this. Really nothing like any other volcano anywhere else in the world. This is not it. This, you might think that's Krafla volcano because it kind of looks like a volcano, but that is subglacially erupted tephra and stuff, pyroclastites. It's not the central complex at all. There are ridges on over there, you can see, and they're behind the photographer in this case, and a big flat bit in between. It's where the island has been spreading out, and there isn't a big pointy peak that smoke comes out of. That's just not the way these volcanoes work. This is somewhere near where the fried egg caldera is expected to be in the magma chamber, but way off in the distance, you can see there some bits of smoke, which was the lava flows. It erupted in a similar way on 2 occasions, 1724 to 29, and then more recently, 1975 to 84. And it was rather unfortunate that it started erupting in the 70s and 80s, because that was just when a new power plant had been established at Krafla. But fortunately, nothing bad happened. And that's what it looks like, kind of a moonscape, really. But you can see the new lavas over there in the distance. And in some cases, there are lava tunnels formed in those lavas. So they are really quite significant and substantial lava flows. So I mentioned there was a geothermal power plant. And nowadays, if you visit much of Iceland, you can have tarmac roads. In fact, there's tarmac road all the way around. And mostly through the middle, but not entirely. So you can see the this is the geothermal power plant, which is tapping into the energy within the magma chamber. And nearby, what you do is you're drilling down and you're extracting very hot waters or steam, depending on how deep you're going and which place. So at Krafla, they're bringing up the steam, turning the turbines, and what you're going to do with the water? Well, for quite some time, they just sort of made a river by just sort of sending it away, and it was horribly polluting and not a very good thing to do. Mostly, they re-inject it, so out of the way. There's always a challenge in doing that because you don't want to cool your reservoir, so you've got to put it back down somewhere convenient. But whatever you do, you end up with too much of this the waste product, which is briny, stinky water, and you always end up with a massive lake like this near a geothermal power plant. And bear that in mind when we talk about the very expensive spa resort of the Blue Lagoon in Iceland later on. Where's it come from? So that's all part of Krafla, and then if we go to the southern end of Krafla, you can see the. Oops, sorry, keep doing that. Every now and then you can see these little pipes coming out of the ground, and then a road, and then some more pipes. So the drilling is done all over a very, very large area, and then bringing the steam down towards the power station to run the turbines. So that's a very useful volcano in Iceland. It's not very conveniently located, however, because it's got lots of power and it doesn't seem to be erupting at the moment, but will continue to produce a huge amount of power in the middle of the country where nobody lives. You can't have everything, can you? The volcano that everybody has heard of, the Icelandic volcano of 2010, Eyjafjallajökull, is located here down at the bottom. And you may remember it's right next door to Katla, which is the big eruption or the big volcano that people are far more concerned about than Eyja, as it's often called. The eruption of Eyjafjallajökull in 2010 was quite pretty, but it was really small. It was not a big deal at all. However, because of so here's Iceland. This is a picture taken from a satellite. This is the south coast of Iceland. This is the plume coming down here to the southeast, and here's Scotland. So it was real, But do you remember looking up into the sky during that eruption and thinking, it's blue, there's nothing up there? It was beautiful weather, wasn't it? It was a freak weather conditions that the wind was coming from Iceland southeast and into the whole of Europe, really, which just we were sort of first in line, weren't we? But it had quite an impact, didn't it? Everybody can remember where they were when that eruption was going. A lot of people have sob stories about being abandoned in Seychelles or, you know, wherever, couldn't get back to Europe. But there were all sorts of economic impacts, and I won't go into it now, but it was a big deal, and people well remember it. And that's probably all people remembered until the most recent eruptions in Iceland. And it was probably because of the impact of this eruption of Eyjafjallajökull that people got really concerned a couple of years ago when Iceland began to hit the news again that there was an eruption happening. But move on to some, okay, so that's the volcanoes we've talked about. Let's talk a little bit about some of the research that I've been doing with colleagues in central Iceland first now. So I've been working at a volcano called Askja, which is located here, pretty much, well, it's called central Iceland. It's pretty much in the middle. Again, nobody lives anywhere near there. And this is the main ice cap just south of it. So homing in on Askja, what does it look like? This is a satellite view. This is scale. Everything is huge in Iceland. So this is 10 kilometers. So 10 kilometers, if you imagine the fried eggs from the early slide, this here's your fried egg, right? This is the yolk here. This is the big caldera, about 10 kilometers across. Pretty enormous. But it is a caldera, it's a round thing. It's just not formed in the way that you often think about a caldera forming, which is by collapse and evacuation of a magma chamber, either because, well, usually because it's exploded out all over the place and then the ground collapses down. These volcanoes, we think, and this was some of the gravity work that we did quite a while ago now, suggested that actually, certainly Askja caldera grew in situ below the ice, because most of Askja was formed really unhelpfully. They call the period pre-post glacial. So you just have to get your head around that. That means when the ice was there. So pre-post glacial, i.e. more than 10,000 years ago or so, or certainly more than 8,000 years ago. So most of these escarpments here were lavas or intrusions that came up underneath the ice and were confined. So they couldn't travel. It couldn't form lava flows because there was ice everywhere. So it would come up out of the ground, it would melt a bit of ice above it, but then be really confined. So that's how you end up with these rather strange shapes in Iceland. So many of these scarps and even these round bits here that make it look very much like a caldera seem to have been formed in that way. Okay, so that's the big caldera at Askja. There are some outer calderas as well here. And this thing here is very important to remember. Öskjuvatn is a lake, and that was formed in the most recent big eruption of Askja in 1875. So that is an explosion crater. It's quite a large crater, sort of 4 or 5 kilometers across and 200 meters deep. It's quite a biggie. So this is how it looks most of the time under the ice and snow. So here's the outer part of the caldera here. That's about 10 kilometers across, remember. This is the lake that's about 4 kilometers across, more or less. And the reason that it's not covered with ice is because it's warm. And over to the north here, you can see a volcano, a pre-post glacial volcano called Heidelberg. And it's rather interesting. If you look at the shape of it, that is the classic table mountain, it's called. So called because it's got a flat top. So it's a volcano with a beautifully flat top. And the reason is, as I was saying earlier, it was trying to erupt. It was all covered in ice. And so the lavas could just come up and then they'd freeze. And then some more would come up and it would freeze. And so it sort of grows out a little bit like that. And you end up with this kind of cylindrical blob. And that is how you make a table volcano. or Table Mountain. And so that's probably the most beautiful one in Iceland. It's certainly the best preserved. So we've got Heidelberg slightly to the north of Askja, and here's Askja itself. Okay, and this then coming down a little bit more, this is sort of what it looks like most of the time in the summer. Here's the hot lake. Here's another tiny little crater that has got much hotter water in it. In fact, you might see some people who just about make out some bodies there. They're just walking down into this stinky water. No idea why they would do that. And we've got lava flows here. And so this is the over here where I'm pointing, that's the northwest corner of the big Öskjuvatn lake. Okay, so what we do, what all geophysicists do is set up places to make their measurements. So all of these various dots and things are places where we've made our measurements. And you have to bear in mind, this is in the middle of nowhere, and there's no road actually into this part. So there's a campsite and stuff way over here somewhere. Little road and a car park comes most of the way up to here, and then you've got to walk. So anything that you want to bring with you to measure, you walk across the lavas and everything all across here. So hence more stations in this bit and rather fewer over in this area. And that is a big problem, natural bias. You go and make your measurements where you physically can do it. Anyway, so we cover the volcano with measurements, and this is the easy bit, getting to it. So, I mean, even the roads in this part of Iceland, this is the 1961 lava. It's quite a small eruption of Askja that I didn't even bother mentioning because it was so pathetically small. But these are the lava flows, and the Icelanders are absolutely brilliant. They want to go somewhere, they'll just bulldoze through the lavas. And these sticks are here to show you where the road is when it's all covered in ice and snow, which it is most of the year. So this brown stuff is the tephra that was erupted in 1875. And that's another complication that there will be for future geologists, because we've got 1961 lavas on top of, well, apparently on top of, 1875 tephra here on top of 1961 lava, because it's blown onto it. So when it's easy, we drive along and we get out and make our measurements groveling around on the floor. So that's the easy bit. And sometimes you've got to walk a little bit further. This is obviously not Askja because there's vegetation. Don't have any of that there. This is obviously Askja. That's what it looks like most of the time. But we do mark our points where we make our measurements like this, so that we can hopefully find them again. So that's me making gravity measurements, and my colleagues make deformation measurements. So they basically use a ruler, which is this one with a barcode on it. It's a leveling staff. And by setting your theodolite in the middle, and you set your, I'm always very rude calling it a ruler. They get very upset, but it kind of is, isn't it? They set it up there. You can see it. It's actually on a little platform there, and it's all marked with the yellow paint. They measure it there, and then as many as you like, but 4 or 5 of those measurements in a circle around your point. So you can tell very precisely, and I mean very precisely, less than a millimetre, how much the area has tipped. And you do that in lots of these stations all over the volcano. And so you can see whether the surface of the ground has tipped at all. Why don't you do this by satellite or GPS, you ask me? Because it ain't so good as doing it the good old-fashioned way. And that really is true. It is more precise at the moment still to do it in this way. Of course, we use GPS as well. The advantage of GPS and INSAR, which is another method, is that you can do a lot. You can cover a much bigger area, and it's quite fast. But if you want precision as to what's going on, and you do need that precision in some places, then you have to be there to make the measurements. Okay, so what has been found? Well, for many, many years, Askja just carried on sinking, and it was getting a bit boring, really. So here's the fried egg. This is the big caldera part here, remember? And this bit here is Öskjuvatn, the big lake that was left after the 1875 eruption. And this little star here on the northwest coast or the northwest shore of the lake, I pointed it out in one of those earlier pictures, that has been the site of ongoing deflation forever. For decades and decades, it has been sinking down by, on average, 6 centimeters a year. It's not much, but when it does it year after year after year after year, that's actually quite a lot. And just take a typical example from 1990 to 2005, it went down by 35 centimeters. One of these is the model, and one of these is the actual data, and I can't remember which triangles give the predictions. There we go, the triangles. So the measurements are the squares, are the crosses, and then you measure that the ground has gone down like this, and so you come up with some models as to what could be happening underneath to account for what you observe here. And then that's your model, and then you work backwards and you say, well, if that happened, what would you observe? And that's how you check that your model fits your observations. So that's why we've got those two slightly different lines. One is what you actually observed, and one is what you would observe given the model that has been made up. So it's not bad. And broadly, what it was deflation of a magma chamber beneath the caldera. So that was the ground deformation, basically going down for year after year after year. The gravity measurements, which is one of the things I was doing, showed really nothing very exciting. So we started in the 80s, and the work is still going on. So from basically 1986 or so through to 2010, all of these stations in the red and the yellow area, which is the central part and the southeastern part of the caldera, nothing happened, pretty much flat. But the stations here at the center of the caldera, so that's right on the northwestern shore of that lake, gravity decreased quite significantly over quite a long period of time. Now, gravity goes down, could be caused by all sorts of things. Usually, if ground goes up, the gravity will go down. And that's because you're getting further from the center of the earth, so you weigh less, gravity is less. So the fact that the ground was actually going down and gravity was going down means that there's a really massive amount of magma or material going from underneath you. So we were all very much convinced that magma was draining from Askja for decades, which is why we got awfully excited just before 2010 when it seemed to reverse, and we thought, oh, it's going to erupt. How very exciting. You have to remember that each one of these points, that's the result of, you know, a whole field season, a whole field campaign of measurements. And so it's all very well with hindsight looking back at these data and saying, well, that was only a little blip. But at the time, you only see that one point. So, for example, in this year, when we saw this point, we didn't know what was then going to happen. That's my excuse. So we got very excited. And our colleagues who were seismologists looked at the small earthquakes that were happening in the area at the same time. This was sort of 2007, 2008. And they were able to identify two types of earthquakes. So here's the Friday, and here's the lake again here, okay? So what they saw was quite shallow earthquakes, that's the green ones, coming from more or less the region where we'd seen this ongoing sinking down of the ground, and this gravity had suggested that not only was the ground sinking down, but magma was being drained away faster even than you needed to account for that deflation. And you were seeing these earthquakes going all the way here over towards Heidelberg, that beautiful Table Mountain, and some much deeper earthquakes slightly to the north, but all kind of parallel to each other. So all very strange, all very concerning. We spent a lot of time out with the Icelanders trying to figure out what was going on, and basically trying to predict where the eruption was going to come out. And it mattered, but not because anybody lived there, but it's a massive tourist resource. People are coming there, particularly in the summer months. Nobody goes there much in the winter. But it was really important to know what was going to happen. And also, of course, if it was a large explosive eruption, it would impact Europe. This was actually before we had the Eyjafjallajökull eruption, but these earthquakes and so on happened. But anyway, it was certainly really very, very concerning. But nothing happened, which is kind of what volcanoes do. You know, they let you down. If we looked to the south, though, so all of that stuff was looking to the north, and do you know why? Because the road came in from the north, and then there was this great big ice cap. Had we but turned around, you'd see this beautiful ice cap, kind of impenetrable, right? You cannot go there and make measurements very easily. This Kyrkfjord volcano is just one of many underneath this ice cap. But then in 2014, Vardabunga, what a wonderful name, decided to erupt. And it had been sitting thinking about it for some considerable time, because this is the ice cap. And you see all those crevasses? It's melted that ice from underneath. This is a couple of kilometers of ice was melted. And then eventually, this white stuff is just steam. This is just melted ice cap. And there's a plane flying in the foreground for scale. It's quite significant. So it did its thing for a little bit. And then the red stuff started coming out. And that came out to the north of the ice cap, i.e. towards Askja. So all very pretty, didn't do anybody any harm, apart from the scientists who had been monitoring to the north, who felt a bit silly. So here's Askja, here's the fried egg, here's that lake, here's where we saw that center of deflation and later gravity decreases as well, and suddenly an increase in gravity. All our attention is up here to the north. We did have some stations came around here, but this was as far as we got because of the ice cap. And this is where the lava actually came out. So there was the big melting of the ice cap itself. That's presumably where the fried egg volcano is, underneath the ice cap. But the lava then came out not underneath the ice cap, way to the north of, here's the ice cap, you can see it. Here's the lava, a long way south of Askja. Well, couldn't credit it, could you? So Vardabunga lavas were still warm in 2016. I mean, that's just an interesting fact, nothing else really. And the cauldron left by the eruption is still there. So it takes quite a long time for the ice to form back again. So if we look at a map of that general area, here's Askja that I've been talking about, and we knew that it had fissures that went way, way up to the north. We know that big eruption that happened in 1875, where the brown tephra went all over the place, it even went over to Scotland, by the way. So, you know, that would have been quite a significant eruption. But we know that lavas that were erupted at the same time came out way, way, way up here in the north. So it is a very elongated system, and that's why these volcanoes are so complicated, because you see stuff going on here does not mean that's where the activity is going to be. The lava, in this case, there was a large eruption here, explosion here, but the lavas went for some considerable time up here to the north. But it also extends down to the south. But in fact, it's even more complicated than that, because although you can color code it on here and you can convince yourself that this is how it is, we saw the precursors going on at Askja, and then it was Vardabunga, which is the purple volcano, that erupted. So are they actually more connected than we thought? Don't know. And literally, we don't know. So what's going on now at Askja? Well, the height changes. So the ground has been deflating for decades. Then between July 21 and September 22, it went up by 40 centimeters. It had been consistently sinking down. So we'd seen years before the gravity change, and now the ground was changing. So again, everybody got terribly excited. And so we've got a little bit more data. Here's the data I showed you before. And it's just helpful to think, at the time, you just see this little blip and you think, gosh, something's going to happen. But then what actually happened? Well, that little blip is this little blip in time here. Basically, it just carried on doing what it had always done with a small blip. But in when was it? Well, 2021, gravity had increased very significantly. The interpretation of that was new magma coming in underneath Askja. So the ground had been going down for a long time. Magma was draining away. We thought to the north, but maybe to the south. But now magma is coming in. We know that from the gravity, and the ground is going up. So is something going to happen? Again, everybody's got terribly excited and gone out and made further measurements. And guess what's happened? Nothing. So this is what it looks like. Well, it's a couple of years ago, but it's what it looks like all the time at the moment. This is the lake, stunningly beautiful. Pre-post glacial lavas here. Here's one of our instruments on top of the station. This is the area. I mean, there are a few stations here, but this is one of the ones you can see here. In that northwestern part of the lake is the beautiful lake, and it's flattened off again. So watch this space. You have to be extremely patient if you want to study volcanoes. Okay, so that's some of my frustrating work in central Iceland, looking at Askja and Bardarbunga, and just thinking about some of the structures beneath the fissures. You can see the fissures on the surface, but what does that actually reflect in terms of dikes and what is linking to what? It's not always quite as obvious as you think, as in one area may actually be linked to a completely separate one. So what's going on at the moment? Well, just a few years ago, there was a lot of excitement because there was some inflation down here in the Reykjanes Peninsula, the southwest of Iceland. Very exciting. Several centimeters a day at some points. The nice thing about using these satellite images or satellite derived data is that you can cover a huge area. And this is, well, it's just showing that there's some ground deformation going on here, and here's the site of an earthquake. But what I wanted to show you on this picture is Grindavik, which you've probably all heard of now, because that was the town that got zapped by the ongoing eruption at the moment. This is Grindavik. 4,000 people lived there, and they were evacuated quite quickly, and then they came back and so on. But it's basically a ghost town. It's had it. That's Grindavik. This is the Blue Lagoon, which is the place where if you want to, you can pay a lot of money to bathe in acidic waters, which are the byproduct of the massive power plant that is located there, which is hugely economically important for the Icelanders, because this is actually where they all live. Nobody cares about the centre of Iceland because nobody lives there. They all live in Reykjavik, and it's kind of around the edges of the island, but in Reykjavik. And if you fly into Iceland, you will come into Keflavik, which is up here. So there is one road that goes from Grindavik, which was actually fairly important fishing point, but you know, here's the road that goes around the coast of Iceland. There's one road that goes up north to the north rather, past the power plant, very important, past the Blue Lagoon, which is this very expensive spa and hotel and everything, brings in a huge amount of money to Iceland, and up to the big international airport, not to mention what was a big NATO base up here. It's now looked after by the Icelanders mainly, but kind of an economically massive deal. So that's why there's a lot of information, a lot of data being collected in this area. So a lot of concern, obviously, when it looked like something was going to happen. A lot of earthquake activity. Just take any random day. This is this could have been taken yesterday, but it was actually a little while ago now. A lot of activity still going on in that southwestern part, but earthquakes happening all over the country, but not randomly. They're following the line of active volcanoes, Askja and Krafla here, down through Bardarbunga and all those underneath the ice cap, down here through the East Rift Zone. This is down to Cirencester and Jaime, which I mentioned earlier on, and some other volcanoes here, well, Katla and Eyjafjallajökull here, and then flipping over to this part here, the Reykjanes Peninsula, which is where it's all happening at the moment. So what happened? Well, so there was a lot of, oh gosh, something's going to happen. Then in 2022, finally, it came out. So you have this ground inflation suggesting magma's coming up underneath the ground, but it being Iceland, it doesn't just come out, it often goes along the dikes. And this was the problem in Iceland. They didn't know where the lava flow was going to come. It eventually, and that's why some of the names in Iceland are really confusing, because they talk about a particular eruption, like this is the Meradella Valley eruption. It's all the same thing. But this is where the lava actually came out in 2022. Looks very pretty. And in the daytime, that's what it looked like. Fantastic tourist resort. It looks very safe. It is safe if you keep off it, obviously. It's best not to actually walk on the lava until it's properly cooled down, because you can get a thin crust forming that you can then fall through if you're not quite careful. So beautiful eruption. Nobody really cared because it was quite a long way to the east. Then the ground uplifted. This was in back end of 2023. The ground uplifted closer, a little bit closer now to Grindavik, 6 centimeters in just a week. That's quite a lot. Remember in Iceland, in Askja, we got used to 6 centimeters a year, and that was quite huge. So 6 centimeters going up is bad, because that usually means magma's coming up. In just a week is bad stuff. So then 3 centimeters in a day. So that's when, evacuation, something bad's going to happen here. And so the eruptions then were called the Sundanika eruptions. This was really, really close to Grindavik, just before Christmas 23. I don't know whether you remember this, but this was when it was all in the news and they had to evacuate Grindavik, and it was all pretty horrific. And then when you see it in the daylight, you can see why it's horrific. But you see, where's the volcano? There is no volcano, but there's a hole in the ground that the lava comes out of. And the lava just goes where it feels like it. It just follows the topography. So it kind of goes down towards the sea. And unfortunately, Grindavik's in the way there. So you can see it's just beginning to impinge on some of the houses and businesses and people's livelihoods there. So in the wintertime, this is kind of what it looks like. So here's the harbour at Grindavik. This is looking back, that lava flow that I just showed you is coming in here somewhere. So this is new lava covered by snow. This is a perennial problem in Iceland. It keeps getting covered with snow and ice. This is the big road that goes up to the north, goes past the Blue Lagoon, goes past the power plant. So really important to keep going. But look at this topography. You've got these old mountains. So these were formed underneath the ice when there was big ice cap. They're not active now. They're not doing anything. But they're kind of in the way, but in the way in a good thing. So that there are lava flows happen, and that's obviously very inconvenient if you live in Grindavik. But also because of the movements of the magma below the ground, it fractures the ground above it. It may not actually come out, it may not actually erupt all over the place, but it still is somewhat disruptive when you get fractures like this going across your street. And this was when it really was kicking off in early 2024. And you can, from this picture, it sort of looks like the lava's coming out everywhere, and it's coming out in a cross. It's not. Remember your plate tectonics, it ain't going to do that. It's broadly that, so wherever the magma is being stored, because Iceland is being pulled apart, the fractures are going to be broadly north-south. So that's where the fissure is going to be. So here's your fissure, and you can see that's a fissure. It's got fire fountains all along it. Okay, so that's an erupting fissure, and bits of the fissure that aren't erupting are going across these streets here. But every now and then, a little bit more comes out, or it just finds a little route, and it makes a lava flow. So the lava can flow wherever it feels like away from the fissure. That's why it's so difficult. If you're a civil defence person there, trying to say, evacuate this part of the town, or that road's safe, but that road's not safe, it's really hard, because you never really quite know where it's going to go. All you can do is look at the topography and do some modelling and hope. So that's what they did a lot. Obviously, they had to evacuate people, and So it's one thing having a fissure going across the road, a bit different if it comes underneath your house. And there was only, as far as I'm aware, only one person died. Obviously, it's one too many, but one person did die in the eruption, and it was down one of these holes. They just disappeared. They were never found. And can you imagine how scary it would be to go down on a ladder trying to look for somebody down there? Absolutely horrific. So this was all sort of Christmas time, and then and the early part of 2024, middle of the winter, very dark in Iceland at this time, trying to predict what was going to happen. What the Icelanders did rather brilliantly, it was what you do at all volcanic crisis situations, is you divide the thing into zones, and you try to say what's going to happen in each zone, and then you say what's the likelihood of it happening in each zone. So obviously Grindavik was quite important at zone 4 here, and in this particular hazard map that they did, this is for the 23rd of April as it happens, they thought it was quite likely that where are we? Zone 4, sinkholes. Well, we saw that, didn't we? Fault movements, gas pollution, and maybe a lava flow. So kind of everything. But zone 3, which was even more, so this was a very high hazard. It said zone 3, this is this whole region here, which is where the main fissure is. So it's really all you can do. And this is the Blue Lagoon and the power plant up here, zone 1, where at this time it was just gas pollution and lava flows. Now, you might think, well, nobody much lives there, who cares? But of course, economically, it's a really big deal. So we need some mitigation measures. So what was done was some walls basically were built. This line here is a wall, and another one here, and you don't have to do, so it's like a ring, a defensive ring, but it doesn't have to be a continuous ring because you've got these convenient mountains. So the lava is not going to go over the mountain. If it's going over the mountain, you're in trouble anyway. Okay, so don't worry about it. But so the walls kind of, do you see there's a big gap here for the road? Always important to have a road, because, you know, that's needed for logistics. But this was the best guess as to where it was best to put the defensive structures, and some more down here to protect Grindavik itself. The defensive walls, various heights and so on, cost about £30 million to do. Big hoo-ha in Iceland about who's going to pay for that. So it basically they're being taxed. So that's how they're paying for it. But the hoo-ha was that the power station is privately owned, so why shouldn't they pay for their wall? So let's not get into that bit of the politics. This is what it looks like. This is the more or less circular wall. Here's the power plant. So it looks quite a small wall, but that's the point. Basaltic lavas, if you look at them flowing, you've seen pictures of Hawaii, Etna, places like that. Apart from when they're on a steep slope, they don't really move very fast, and they're not really very scary, and they're quite easy to put off. Put a little barrier in their way, and they'll go somewhere else. And that has certainly been the hope. And I think this next one is a movie which is just about showing. So this shows how this just happens to be in April 24. So here you can see the barriers, and the lava actually came out from a vent way up here and then flowed towards these defensive barriers, and you can see it getting thicker. It sort of built up behind the defensive barrier, but didn't overtake it. Even if it does overtake the barrier, it buys you time, and that's the thing. So there's that mitigation that's been going on in Iceland and is still going on. And the other thing that you can do to try to mitigate is to make an attempt at predicting how, because it's one thing predicting when an eruption is going to start. It's almost as important and certainly as difficult to say when it's going to finish, because that has massive economic consequences. If you're going to evacuate a town, that's quite a big deal. It's quite hard to do. People don't want to go. But if you say it's for a week, okay, fine, they might go. If you say, well, I don't know how long it's for, it's much more difficult to get people to engage with it. So the more evidence and scientific backing behind what you're asking people to do, the better, particularly with a very well-educated population as the Icelandic population is. So one of the ways they were doing this was looking at plotting the days since the beginning of new inflation of the ground against the amount of magma that they calculated was doing that. So as the ground goes up, you can sort of calculate how much new magma is coming up underneath you. And the rate at which that happens gives you some indication of how fast or how big the eruption is going to be and when it's going to be. And each of these stars, now what are the stars? Oh, so each of these are episodes that were measured. So each of these little dots is a measurement. Where it finishes in a square, it was a dike was formed. So the ground went up because a dike went past, basically. Where there's a star, it means there was an eruption. So broadly, the longer it's been going on, the more likely it is that you will have an eruption of lava. It doesn't always work. This event here obviously didn't take very long for an eruption to actually occur. But that's the type of measurements that you can do. You can also look at how long it's been since the last eruption, and assuming more or less that the same amount of magma is coming into the system all of the time, you can predict how big the eruption is going to be, because broadly, the longer you wait, the worse it's going to be. And probably the most helpful way of looking at this is as a timeline. The further along the timeline you go, there's a lower boundary and an upper boundary, and the eruption is likely to happen after a certain amount of time. And so you can say the eruption will happen sometime in the next 3 weeks, and it will have started by the end of 3 weeks' time. So that's quite a new helpful thing to be able to say to people. Trouble is, people get very bored very quickly, and so these maps were being produced all of the time, every month or so. They kind of began to look a bit similar, and people weren't really taking too much notice. And basically, it was always the same. It was always saying Grindavit's doomed, and hopefully everything else is kind of okay. And so what they've started doing now, and this is the current map, and this is valid until the 18th of June, so you're okay till then. What they've done is divided it into zones, A, B, C, D, and so on. So here's Grindavik, zone A, and it's seismicity, sinkholes, fault movements, kind of same as, and that's why it is a ghost town now. Svartsengi, which is that's where the Blue Lagoon is, and the power plant, that's B, seismicity and sinkholes and fault movements, not lavas, and so that's a green zone now. That's a low hazard. So right now, and at the moment, this is valid until the 18th of June. Obviously, if something suddenly happens overnight, they'll have to update this. But politically, I mean, these are political statements, these things. What this is saying is Keflavik's fine, nothing to see here. Do fly in, do come and see us. And that does seem to be the case. It seems to be the walls that they have built at quite large expense do seem to be doing the job, and they are continually rebuilding the walls and making them taller, the structures to divert the lavas. Last week, Etna was in the news, wasn't it? Wasn't it amazing? And I just thought that you might be interested in a comparison with that, just very briefly. Because that was a big explosive eruption, and it was really scary, obviously, for the people who were up on the summit there. But apart from brief explosive eruptions, I mean, if you have a massive explosive eruption, there's nothing you can do, right? If Vesuvius does what it did in AD 79, you're not going to run away from that. That is what it is. But you can. Let's just try and mitigate what we can mitigate. We can mitigate against some lava flows. So you may not remember this, but in the early 1990s, there was quite a lot of lava flow activity going on Etna. And actually, it's quite similar to the lava flows that were also erupted during this eruption on Iceland, on Etna a couple of weeks ago. And during this period in the early 90s, we were involved with the Italians in making measurements, and not so because the eruption had already started. What mattered was when it was going to finish, because that affects the civil defence expenditure. So I just mentioned in Iceland, they spent £30 million building these defensive walls. The Icelanders, the Italians also had some mitigation strategies for this lava flow in Etna, but they wanted to know, is this lava going to erupt for another week? If so, fine, we can deal with it. We'll build things here, there, and that's fine. Or is it going to last for months or years? Because it's a very different mitigation strategy. Are we going to evacuate Sicily, or are we going to close Catania Airport forevermore? Or are we just going to ride this one out? So that's what we were trying to do, was to use, again, gravity. They sort of dropped us off helpfully up the top of the Etna, quite high up there. They never did come back for us. So we had to make our measurements and make our own way back down again. And the reason they didn't come back, they probably forgot about us, but the main reason was that they went further back down, and that helicopter was being used to collect these concrete blocks. And it would pick them up and chuck them onto the lava. And the idea of that, onto the lava flow, and the idea of that was to break the crust, because a lava flow that, you know, when it's going and it's really going places, the top will freeze, and that's, of course, that's how you make lava tunnels. The inside bit will continue to flow, and that's your problem, because that just keeps warm. It's insulated by the top bit that is frozen. It will continue to flow, and it can go a lot further. So the idea was to chuck concrete blocks on the top of the lava flow to break up the surface so that the heat would be dissipated more rapidly. What actually happens in this particular instance is the concrete blocks floated quite nicely down the hill. So that bit didn't work quite so well. But a combination of building barriers, a bit like the Icelanders have done, building barriers, actually trying to blow up the lava flow, which was quite spectacular, I can tell you, trying to do that, and chucking blocks in some other bits of it that were a bit more susceptible, because if the frozen carapace is too frozen, even throwing a concrete block on it doesn't do any good. But in some other parts it was more effective. But a combination of all of those did save the town here of Zaffarana. Of course, we'll never really know, will we? If they hadn't done any of that, would Zaffarana have been destroyed? Who knows? The owner of this house thought so, but this was mostly not the case. This was just a rather funny example, but unless you owned a house, obviously. But the town itself was safe, and it was all fine. And so people have been trying to mitigate against eruptions forever, and it's very expensive and it's very hard. And I don't envy anybody whose job it is to make the decision as to how much you're going to spend and where you're going to spend it. So it's rather nice to fly in and make some measurements and get out again. Okay, so I said I'd talk about the present of Iceland, which I've done. What about the future of Iceland? Cirencester, remember, erupted between 1963 and 1965. It's not erupted since. So the only thing that has been happening to Cirencester is it's been eroding, and quite spectacularly, actually. So between 1967 and 1974, the coastline was eroded really quite significantly. So this is the blue bit here that's broadly what's left. And it's changed shape quite a bit, but its coastline has been quite eroded. The most recent measurements in 2019, at least the most recent that I've got, show this is the outline of the island. So at this rate, 100 years' time, there will be no Cirencester. So take a look while you can. It's not a place that they allow visiting, but you can see it from the other Vestman Islands, and you can fly over it and stuff, which is quite cool. So we're thinking there about the present and the future of Iceland, and thinking about eruptions and intrusions and how they continue. And basically, when the erosion rate exceeds the eruption rate, the land mass is going to decrease. Plate tectonics in Iceland, as I said it right at the beginning, is really complicated because you've got the combination of a plume and a spreading ridge. If it were just the spreading ridge, Iceland wouldn't exist. I mean, there'd be volcanoes and so on, but they'd be down below the level of the sea. So it's only because of the proximity of the spreading ridge, of the plume. So as the spreading ridge moves away from the plume, it's likely that the activity, I mean, not in our lifetimes, it's okay, we'll still be able to visit it, but in due course, Iceland will just be an anomaly and there won't be anything of it. And there's nothing we can do about that. And there's nothing we can do about large explosive eruptions either, but we can mitigate some of the effects of certain types of eruption. I know it's a lot of caveats there and it's all a bit, naff, but there are some things that we can do in the short term about volcanoes. So I think that's it, really. I think we've more or less answered those questions. So
absolutely fascinating. Time's really getting on, and we've got an AGM to have and a social to have. So I'm only going to allow one question because, I mean, I'd love to keep her here for another half hour, but I know she's got a long drive to do. So let's just have.
I know the island of Montserrat very well, and about 50 years ago, they had a catastrophic volcano that more or less obliterated half the island, largely through pyroclastic flow. It seems the way you're talking that forecasting whether that volcano will be erupting again is more or less impossible.
Well, is it impossible? It's a lot harder than, I mean, the thing about volcanoes is you mostly sort of know where they are, apart from in Iceland where you don't know where it's going to come out. So we know Montserrat is a volcanic island, so we know it will erupt again. So we could throw a lot of monitoring at it, and that would help us to make measurements, but to make measurements and therefore predictions. But there are, 600 or so active volcanoes right now. And the vast majority are not being monitored because it's too expensive and we can't. Increasingly, we can do this sort of thing from space, but there's not a lot you can do. You can look at some of the ground deformation and some heat measurements sometimes when the clouds aren't there. So it's quite hard. So I don't want to imply that there's nothing we can do about predicting eruptions, but it's disappointing. It is disappointing, yeah.
They do have a monitoring thing full time though.
Of course, yeah. And many places do. Montserrat's largely got it because it's a British dependency, and because of its history. Huge number of places just aren't monitored at all, which is arguably a lot worse.
Okay, thank you. As I said, I'd love to keep you here for another half hour, but we've got quite a lot to do
Yeah, sure.
yet for the rest of the sea. So thanks very much indeed. That was absolutely fascinating.
You're very welcome.